We will now see how the arbitrage pricing theorem yields a bond pricing formula in terms of the short rates. Indeed, the earliest interest rate models, which date back to the 1980s, were short rate models. The most prominent among the two are the Vasicek model and the Cox-Ingersoll-Ross model. They're both still very much in use. They both come with their strengths and their limitations. Limitations are that these models produce forward curves which are low parametric. And we have seen that this poses problems when fitting to a given term structure. We remedy this by adding a time inhomogeneous term, and that leads us to the Hull-White extensions. We now focus on the risk-neutral measure Q and assume given an adapted short rate process R. The arbitrage pricing theorem implies that the discounted bond prices follow martingales and Q. And that has to hold for any maturity capital T. Using the fact that the terminal value of the T bond is 1, and using the defining property of a martingale being the conditional expectation of its terminal value, this leads us to this bond pricing formula. So the T-bond price is the conditional expectation under the risk-neutral measure of the exponential of the time-integrated short-rate process. This is not very explicit, and we ask what are the dynamics of the T-bond price processes that we get. Well, this will depend on the model for the short-rate process under the risk-neutral measure Q, and if on top of it we are interested in the dynamics of P under the real-world measure P, we also would need to specify the market price of risk lambda, which brings us back from Q to P. The first model we consider is the Vasicek model. The Q dynamics of the short rate is as shown here. This model has 4 parameters. Kappa is the mean reversion speed, theta is the mean reversion level, and sigma is the volatility. The 4th parameter, don't forget, is the initial value of the short rate, which is not shown in the differential notation. As we will see on the following slides, this is a Gaussian process that mean reverts to the level theta. The figure on the right-hand side shows a simulated trajectory for these parameters as shown here. The mean reversion level is 8%. The process starts at the value 6%, and we see that the mean reversion forces it to tend to the mean reversion level of 8%. This trend is superposed by the martingale part that is larger the larger the sigma parameter is. We can solve the stochastic differential equation shown on the previous slide for the short rate process RT using the variation of constants formula. It shows that the solution can be written explicitly in integral form as shown here. Again, you may be familiar with this fact from real calculus for this part of it. Overall, you can verify the validity of this expression by just applying Ito formula. This expression also shows that RT is a Gaussian process with mean function equal to the deterministic part of it and the covariance function as shown here. When t tends to infinity, we see that the mean tends to theta, and the variance, when t1 is equal to t2 is equal to t, tends to sigma squared divided by 2 kappa. Indeed, the limiting distribution of the short rates is normal with mean theta and variance sigma squared divided by 2 kappa. Now what about bond prices in the Vasicek model? We proceed to calculating bond prices in 2 steps. The first step is to show that the time-integrated short-rate process is a normal random variable, and we determine its characteristics. We proceed by plugging in the solution for RS that we saw on the previous slide, and it gives us the expression here on the left-hand side in black. We next manipulate these expressions in 2 steps. First is we change the order of integration as shown here. We apply that to both the drift term and the stochastic integral term. We then do for both parts as shown here in the first part, multiply with e to the minus kappa t and multiply with e to the kappa t again. We then realize that this integral is equal to b cap t minus small t, where the function b is defined as integral of e to the minus kappa s. We further realize that e to the minus kappa t r0 is the first part of the expression for the short rate RT as shown on the previous slide. We get the other 2 parts from the drift integral and from the stochastic integral so that we can summarize and get this first summand on the right hand side here. We also get these 2 terms as shown here. Using the dependence of the increments of the Brownian motion, we realize that the stochastic integral is independent of ft and it is normal with mean 0 and variance given by the integral of the square of the integrand with respect to du. The first 2 terms are measurable with respect to ft because the short rate process is adapted. These observations imply that the time-integrated short rate process, conditional on ft, is normal distributed with mean given here and variance given here. The bond price, remember, is the conditional expectation of the exponential of the time-integrated short rate process with a minus sign. We have just seen that this exponent is normal distributed, we know its mean function and we know its variance. So we can use the moment generating function for the normal distribution, plug in the ingredients, and arrive at the expression as shown on the right hand side here, where the function a is defined here. Summarizing, the Vasicek short rate model yields exponential affine bond prices in the prevailing short rate RT, as shown here. The functions a and b can be shown to solve the 2 coupled ordinary differential equations, which are quadratic. This is why they are called Riccati equations, along with initial conditions 0 and 0 for A and B. The next short rate model we consider is the Cox-Ingersoll-Ross model, in short CIR model. The Q dynamics of the short rate looks similar to the dynamics that we have for the Vasicek model, except that here the volatility of the short rate process depends on the square root of the short rate itself. Again, we have the parameters theta, the mean reversion level, kappa, the mean reversion speed, and sigma, the volatility. For technical reasons, we have to assume that kappa times theta is non-negative. In contrast to the Vasicek model, we cannot write down the solution to this stochastic differential equation. But it is a mathematical fact that there exists a unique non-negative solution for any non-negative initial values. We illustrate a simulated trajectory of the CIR short rate process for the same parameters theta, kappa, and sigma as for the Vasicek model. Again, we start at the level of 6%. Again, we have mean reversion. But this time, the volatility is smaller because we use the same sigma, which has to be multiplied with the square root of the short rate to give the total volatility contribution. These parameters, of course, have only illustrative character. They would have to be calibrated to specific given market data conditions. Albeit, we cannot show it from first principles as we did in the Vasicek model. We claim that the CIR short rate model also yields exponential affine bond prices in the prevailing short rate, as shown here. The functions a and b solve again a coupled system of differential equations, which are quadratic, so Riccati equations, along with initial conditions 0 and 0, as was the case for the Vasicek short rate model. The solutions a and b for these Riccati equations are given in closed form. They are shown on the slide here. We now prove the claim that the CIR model yields exponential affine bond prices, and we use stochastic calculus. The claim is written here in black. We multiply both sides of this claimed equation by the red factor. This way, we get rid of the small t dependence of the argument in the conditional expectation on the left-hand side. We call this argument M capital T. Just looking at the left-hand side, we realize we have a martingale. We label the expression on the right-hand side by M small t. By Ito's formula, this can be seen to be an Ito process. We also see, because of the initial conditions on A and B being 0, that M capital T indeed coincides with the argument on the left-hand side. Hence, in order to prove equality between these two sides, it is now enough to prove that M small t is a martingale. We do this by applying integration by parts and the Ito formula to M. A few lines of stochastic calculus shows us that the drift of dm, which we already divide by m because it factors out, equals the expression that is given here. Now both components of this sum are 0, and this is due to the fact that A and B satisfy the Riccati equations shown in the claim. This proves indeed that M has 0 drift. In other words, M is a martingale. Both models, the Vasicek and the CIR models, yield closed form expressions for the bond prices. It can also be shown that they yield analytic expressions for option prices on bonds. This explains why they are very popular. these models also have a weakness. In both models, the forward curve is given in closed form in terms of the functions a and b. Now the functions a and b are determined by the parameters kappa, theta, and sigma. If we count the initial value of the short rate as a fourth parameter, shows us that the initial forward curve produced by either model, the Vasicek and the CIR, is 4-parametric. The problem that comes with it is that these models do not fit the data in general. This is illustrated here for the CIR model with these parameters. The red is the implied initial forward curve, which cannot match the observed data points in general because of its low degree of freedom. Fortunately, there's an easy solution to it. The idea is to add a time inhomogeneous component to it with infinite degree of freedom in such a way that you preserve the analytic tractability of the model on the other hand. Here is how the idea works. It is illustrated for the Vasicek model, but it would equally well work for the CIR model and in fact for any diffusion short rate model. We need two ingredients. The first is an auxiliary simple Vasicek model as shown here. We assume that the initial short rate matches the data. In blue, we indicate a given initial forward curve. As we well know, the Vasicek model yields closed form exponential affine bond prices for functions a tilde and b tilde given in terms of solutions of Riccati equations. The second ingredient is a deterministic shift function phi t with zero initial value. We then get a time inhomogeneous short rate model RT as the sum of phi t plus the auxiliary simple Vasicek model R tilde. Notice already that this short rate model matches the initial short rate by construction because phi 0 is 0 and R tilde 0 is the desired initial value. The bond prices are still given in closed form. This is a simple consequence of this observation done here. From this, we easily infer that the model implied initial forward curve is given as shown here. And now it is evident that we will obtain a perfect fit of the given initial forward curve whenever we choose the red function phi as the difference of the given initial forward curve minus the model implied forward curve from the auxiliary Vasicek model. What can we say about the dynamics of the time inhomogeneous short rate process RT? Let's illustrate this for the Vasicek short rate model. So assume R tilde is the auxiliary Vasicek short rate model as seen on the previous slides. We then simply differentiate the sum of phi t plus R tilde t to get the differential of R in this form. We then replace R tilde by R minus phi, and it follows that RT has a decomposition as shown here, where now the theta is a t-dependent function given in terms of phi this way. It becomes evident that we just obtain an extension of the Vasicek model by making the constant theta a time-dependent theta. This extension is also called the Hull-White model. In sum, the Hull-White model yields closed-form exponential affine bond prices and at the same time matches any given initial forward curve.